2-24 was deriving the conduction equation for this cylinder. So we assumed it was steady state, constant K, constant E dot gen in one dimension. It's only varying in R and it's only conduction. So we start out with the energy balance, or just a balance in words, and then convert it to terms. So that, and then it's set equal to 0 since it's steady state, and then using Fourier's law, because it's conduction, and plugging in what we had before into that, and then applying the limit after dividing by the volume, and then you get your derivation. For 2-66, it was an absorber plate that had insulation on the bottom, so it gives us all these quantities. So you assume that the conduction is steady and one directional, and then to use the radiation equation, the surroundings are a black body and the plate is a gray body. Again, constant K, but this time there is no E dot gen. And then at the top surface where we're calculating, there's convection, radiation, and incident solar radiation. So we're finding the net heat transfer. So we started with the second derivative and then integrated down to get a linear expression, and then you apply the boundary conditions, which is a constant heat flux because it's perfect insulation, and then you're able to solve for C1 with that, and then you also have a constant T boundary condition, which gets you C2, and then you plug into this equation that's for the net, so incident radiation, normal radiation, and convection. And then for 14-40, you have a cup of water sitting out just in a room, so it's going to be water and air interfacing, and we know the temperature and pressure, and also that it's 100% humidity, which means that it's saturated air, and air is dilute in water, meaning it doesn't, not a lot goes in, so Henry's law is applicable. They're in equilibrium, and both are assumed to be ideal gases. Properties were looked up, including the saturation pressure of water, Henry's constant for air, and then the molecular weights of both. We know that the saturation pressure of water is equal to the vapor pressure of water, and then we are able to solve for the fraction of water vapor by doing that vapor pressure over the ambient pressure, and then you can just use this and subtract that from the ambient pressure to get the pressure of the air, or the dry air, basically the air vapor, since those are additive, and then you apply Henry's law to solve for the liquid air, basically, or air that is in the water, and that's very small, like it's supposed to be, because Henry's law is only for dilute gases.